Hello, today we're going to talk about forces. Objectives for this module are that you will be able to resolve a two-dimensional vector into its component parts, and that you'll also be able to add two-dimensional vectors using both Cartesian vector notation and normal vector notation. This is specific to forces that are coplanar, which means that they lie in the same plane. Everything on Earth experiences forces acting upon it. Therefore, as civil engineers, our designs must consider the forces acting on a body. Vector addition is needed for applications such as making sure that columns don't bend or break due to unbalanced forces. Meaning, if you design a bridge that doesn't consider the force of the wind and the water, then the bridge will be battered and eventually collapse from these extra forces. Forces are vectors, which means that they are defined by their magnitude and directions versus scalar quantities such as distance or length. These are only defined by their magnitude. For vector quantities, I will use either bold font or the variable with an arrow over the top. For I, J, K, or unit vectors, I will be using a caret, which is a hat above the I, the J, or the K. Other vector operations include multiplying or dividing by a scalar. When drawing forces, the length is typically defined by the magnitude of the force. So if you have a force A and multiply it by a scalar quantity, let's say 3, the result is a force that is 3 times the original force. Notice the arrows above the A indicate that this is a vector. Similarly, multiplying by a decimal or fraction will shrink the force by the scalar amount. In this example, A shrinks to 30% its original magnitude. Lastly, if you multiply or divide by a negative scalar, the force changes direction. This is especially important. Notice that we don't write negative 0.3a. This is because magnitude cannot ever be negative. Instead, we would indicate the direction graphically as shown here. Now to the mechanics of vector addition. Graphically, we can utilize the parallelogram law or the triangle rule. Suppose you have two forces, A and B, that you want to add. You first join at their tails. Next, you draw a line from the tip of B parallel to A. Draw another line from the tip of A parallel to B. Note where these two parallel lines intersect. Lastly, draw a line from the tails of A and B to the point of intersection. That right there is the resulting force, R. If instead we want to use a triangle rule, we just need to keep in mind tip to tail, always tip to tail. That is, first you join force B at the tail to force A at the tip. Then draw a line from the tail of A to the tip of B. The resulting force, that's R. Similarly, you can join that tail of force A to the tip of force B. Again, drawing a line from the tail of B to the tip of A results in R. You should be aware that all of these methods result in the same magnitude of R. Now suppose we have rope pulling the truss as shown. The force along the rope is a vector that can be split into its component parts. We want to know how much force that rope is exerting on the two sides of the truss. We can resolve B into B of U, a force acting along the U-axis, and B of V, a force acting along the V-axis. This process is the reverse of the parallelogram law. When we resolve forces into their component parts, it is useful to represent them in Cartesian vector notation. This notation splits the force into magnitude and direction. The direction is indicated by unit vectors, which define which axis the force acts along and are shown as variables with carets. If the force is acting in the negative direction, the magnitude will still be positive, but the unit vector will be negative. When using Cartesian notation, you don't have to indicate the direction graphically as you would if you were using normal vector notation. To convert between the systems, first resolve the resultant force into its component parts. F of x and f of y indicated here as vectors with arrows above the variable. Then, taking only the magnitude, multiply the x component by I caret and the y component by j caret. Then you have the vector f equals f of x times I caret plus f of y times j caret. Lastly, one thing that you need to keep in mind, it's very important and will really come in handy as we analyze our more complex systems. As long as your x and y axes stay at 90 degrees, you can rotate that axis in any direction to finish your analysis. Now let's extend this to a system with more than one force for addition. You can definitely do this graphically as we've seen before, but more than two vectors becomes extremely difficult to track. In this system, we have four forces acting on a single point. This could be something as simple as the hot air balloon we saw at the beginning of this video. We would first resolve each one of the forces into their component parts and convert them to Cartesian vector notation. Next, we simply add all the components associated with I caret, which will give the resulting force component along the x-axis. Lastly, we sum up all the components associated with the j caret, which is the resulting force component along the y-axis. Adding these two vectors together using either the parallelogram law or the triangle rule is equal to the resultant force, or the force resulting from the two components simultaneously acting on a point. To take the I component and j component back into normal vector notation, we just need to apply the Pythagorean theorem. The resultant force is always, I cannot stress that enough, the hypotenuse. Therefore, the square root of a squared plus b squared equals c, where c is the hypotenuse, and a and b are the two sides. The angle, as written here, is relative to the x-axis. But if you want to find theta relative to the y-axis, you should just apply trigonometric rules. Let's work problem 2-1 from the 15th edition of Hibbler. The problem statement is to 1. Find the resultant force, and 2. Find the direction of the force theta when theta is measured from the positive x-axis to the line of action of the resulting force. We're given the system provided with two forces. F1 is 260 pounds up and to the left with an angle defined by a small slope triangle with a 12-unit vertical and 5-unit horizontal. This results in a 13-unit hypotenuse. The second force is 310 pounds acting down and to the left at a 45-degree angle measured down from the negative x-axis. The governing equation or fundamental equation that we need to solve this problem is that the resultant force is equal to force 1 plus force 2. We'll need to use a graphical method for this problem. Remember, tip to tail. Place F2's tail at the tip of F1 and join the two forces to form a triangle with a hypotenuse of FR. Then use the law of sines and the law of cosines. Therefore, the resultant force is equal to the square root of F1 squared plus F2 squared minus 2 times F1 times F2 times the cosine of C. Drat. Okay, I wrote plus here, but don't worry, I fix it when we work the solution. Remember, the internal angles of triangles should sum up to 180 degrees. Next, apply the law of sines, which is F1 divided by the sine of A, and that's equal to the same ratio of F2 divided by the sine of B, which is equal to the same ratio of FR divided by the sine of C. Now for the solution. To solve this problem, first draw a diagram of what the force triangle looks like. Starting with your first force, you draw that. Then I want you to notice here that you have a 5, 12, 13 small slope triangle, and it's relative to the horizontal axis. So I'm going to draw these dotted lines to indicate that. Next, place the second force at the tail to the tip of the first force. The second force is at a 45-degree angle down and to the left relative to the horizontal, again indicated here by the dashed line. Connecting the tail of the first force to the tip of the second force gives the resultant force. The resultant force is at an angle with the horizontal, but we actually don't know what that angle is. That's what we're trying to find out. Okay. However, once you find that angle, it represents the angle that your resultant force makes with the negative x-axis. But actually, the problem statement wants us to find that theta, which is from the positive x-axis counterclockwise. So to start, let's first transform the small slope triangle into an angle. The horizontal is 5, the hypotenuse is 13. So if we use the cosine of theta is equal to the side adjacent to the angle divided by the hypotenuse, then that'll give us b as the arc cosine of 5/13, or 67.38 degrees. Next, calculate c. Again, the sum of the internal angles in a triangle has to be equal to 180. So I'm going to draw a line perpendicular to the horizontal at C, and then we can calculate 90 minus 45, which is the angle between the horizontal and our F2. And then we want to add that to 90 minus 67.38. That'll equal that internal angle, and it's equal to 67.62 degrees. Now that you have that internal angle, you can use the law of cosines to calculate your resultant force. So that's equal to the square root of 260 pounds squared plus 310 pounds squared minus 2 times 260 pounds times 310 pounds times a cosine of 67.62 degrees. This gives a resultant force of 320 pounds. Now it's best to redraw the force triangle so that you can clearly see what you've already calculated and what you still need to calculate. So the problem statement, of course, we've already calculated our resultant force, but we still need that theta. So now you have the internal angle at the top of 67.62 degrees, and the angle at the bottom is 67.38 degrees, again measured from the horizontal. So it's not the internal angle, it's measured from the horizontal. Therefore, you need to calculate beta, which is the internal angle. So once you calculate beta, you subtract that from 67.38 degrees, and that gives you alpha. Then, once you have alpha, subtract it from 180, and that's your theta. So first calculate beta using the law of sines. Therefore, 310 divided by the sine of beta is equal to 320 divided by the sine of 67.62 degrees. So beta is equal to 63.61. Now alpha becomes 67.38 minus 63.61, which gives us 3.77 degrees. So looking back at the original diagram, you can see that the 3.77 is actually acting in the direction of our resultant force with respect to the negative x-axis. We want it with respect to the positive x-axis. Then theta is equal to 180 minus 3.77, which gives us 176 degrees counterclockwise from the positive x direction. Therefore, your answer is the magnitude of your resultant force is 320 pounds, and it is acting 176 degrees counterclockwise from the positive x direction.